Hi everyone. This is going to be the last lecture for the 7th module. It's going to be a shorter one too, a fairly short one. I just wanted to finish up talking about the adequacy proof, the adequacy of the tree method for SL. And then just a few more comments, and that'll be it for the week. So just to remind you, so this is the handout called the adequacy of the tree method. To prove that the tree method does what we're using it to do, that it's adequate for the purposes that we're using it, we saw that we wanted to prove this proposition. There is an open path through a completed tree for a set of sentences of SL, if and only if some truth value assignment, that there is a truth value assignment, if only if some truth value assignment makes all the set members what I called the initial sentences in the handout, the initial sentences of the tree, true. Okay, so this was an if and only if claim. And this is something that obviously we were taking for granted as we worked our way through chapter 4. But I thought it was worth sort of taking a step back and thinking about this on an abstract level. Why is it the case that this proposition number 1 is true? And we saw that in order to prove this, we actually needed to show two conditionals to be true. First, if this is true, then that is true. And then if this is true, then that is true. And I worked through in detail the proof that goes in this direction, that if there is an open path through a completed tree, then there is a truth value assignment that makes all the set members true. In other words, if you've got your set members and you do the tree for the tree could be whatever. Some stuff could be open, some stuff could be closed. But if there is an open path through this completed tree, then that guarantees that the set members form a consistent set. In other words, there's a truth value assignment that makes the set members true. That's what we mean, right? That the set is truth functionally consistent. And what we saw in the proof is that this direction relied on the upward correctness of the rules. Ensures the only if direction. Sorry, I just want to make sure that you understand what I mean when I say the only if direction. That is, if this, only if that. In other words, if there's an open path through the completed tree, then the set members form a consistent set. Then there is a truth value assignment that makes all the set members true. And what we saw is that the upward correctness of the decomposition rules were crucial in showing that it's true in this direction. And that's what I labeled proposition number 2, and then eventually that morphed into proposition number 4 when I did the proof by mathematical induction. But the level at which I want you to be able, I really want you to understand this, and I'm hoping that you could follow along with the details of the proof by mathematical induction. But the level at which I want you to understand this is to understand the role that the upward correctness of the rules plays in this part of the proof. And just to remind you that along this open path, you're going to have, at least one literal, and that that this open path is going to describe a truth value assignment that's designed to make the literals true. But if the literals came from something more complex, the upward correctness of the rules ensures that the truth value assignment designed to make the literals true is going to make that more complex sentence true. And if that was generated by an upwardly correct rule applied to something farther up the branch, then the upward correctness of the rules guarantees that that's going to be true in the truth value assignment all the way up to the set members. So the upward correctness of the rules ensures the truth of what I'm calling proposition number 2. And also we showed something stronger than what we needed to show. Not only does an open path through a completed tree guarantee that the set members are true, that there's a truth value assignment that makes the set members true, it actually guarantees that there's a truth value assignment that makes every single sentence along that path true by the upward correctness of the rules. You kind of work your way up the path. Okay, the other direction, and I'm not going to go through the details of this part of the proof. This is in the handout. It's the proof of proposition number 3, which is on page 5, I think, of the handout. And so proposition number 3 is in the other direction. It's in the if direction, namely, if a truth value assignment makes all the initial sentences true, then it makes all the sentences on some path true. Some path of the completed tree. True. And that is going to be, that's somewhat stronger than this direction, that if there is a truth value assignment that makes the set members true, in other words, if the set is a truth functionally consistent set, then we're guaranteed that there's going to be an open path through the completed tree for that set. Okay? But this is what I've labeled proposition number 3, and it's a little bit stronger. In other words, if the set is a truth functionally consistent set, that is, if there is a truth value assignment that makes all the set members true, then there will be some open path. Whoops. Then that truth value assignment will make the sentences, all the sentences on some open path of the tree true. So it's just the other direction. So if you've got your set, right? You've got your set members. You're doing the tree for it. And if the set is a truth functionally consistent set, if the set is a truth functionally consistent set, that is, if there is a truth value assignment, why can't I not write consistent set? If there is a truth value assignment that makes your set members true, then you're guaranteed that there's going to be an open path through its completed tree. Not only that, again, this is the bit that we're showing is a little stronger than what we need to show, that truth value assignment is going to make every single sentence along that path, that open path through the completed tree, true. And the proof of this is actually also by mathematical induction, and I work that out. I give you that proof in the handout, but I'm not going to take the time to go through the whole thing. But that's going to be also on induction on the number of sentences that you've decomposed or checked in the construction of the tree. And for this direction, it's going to be the downward correctness of the rules that guarantees the truth of number 3. And, in broad strokes, in this direction. So it's the downward correctness of the rules that guarantees the truth in this direction. And in broad strokes, that it's going to be sort of just like what we did in the proof of the other direction. Namely, if you've got your set members, right? And suppose you've got some truth value assignment that makes your set members true, okay? Now, when you decompose the set members, suppose the set members are more complex than just literals. If they're just literals, then you're kind of done, right? But if the set members are more syntactically more complex than just literals and you have to decompose them, the downward correctness of the rules guarantees that what is generated, at least one list of conclusions that's generated by the downward correctness of the rules, is going to be true on that truth value assignment. And then if you decompose one of those sentences, then the downward correctness of the rules is going to guarantee that at least one list of conclusions that's generated by the downward correct rule is going to be true on that truth value assignment, and then you work your way all the way down this open branch. And so you're guaranteed by the downward correctness of the rules that a truth value assignment that makes the set members true is going to make true all of the sentences along some completed open branch of the tree for those sentences true as well. Okay, and you can read through that part of the proof. At this point, I imagine some of you are thinking, there's not a quiz this week, and you're thinking, oh, wait a minute, is there going to be stuff about what we've done during this interlude on the next quiz? And yeah, possibly. And now you might be thinking, well, what kind of thing might she ask us on a quiz, where she might, probe the extent to which we understood what happened during this interlude. So what do I expect you to understand? I'd like you to have understood again, in broad strokes, the proof that we did, or I alluded to or described, for the truth functional completeness of the set of connectives not, and or. That we showed that not, and or are sufficient for expressing any truth function at all. So there was a whole lecture in which I talked about truth functions and how we can represent truth functions by these truth schemas, and how we can apply an algorithm, and application of that algorithm will give us a sentence. So given any truth function, we can construct a sentence of SL that expresses that truth function. And we looked at several examples of applying the algorithm. I'll just do one really quickly for you here. So let's suppose you have this truth schema, say that it just has it takes two arguments. The function that the function that the truth schema is giving you just takes two arguments. So remember that these are the arguments of the function, of the truth function. And then on the right-hand side of the vertical line, we've got the value that, and here's going to be the values the function yields when applied to those arguments. I'm just reviewing what I did in a full lecture. In this case, the pair of arguments. It's a two-place. This is a two-place truth function. And suppose that it's that it yields the value true when applied to true, true, and it yields the value true when applied to false, true. and otherwise it yields the value false. Well, the algorithm tells us that we look at those two rows of this schema, right? And we label the leftmost row A, and then the next one B, and if there were 3, C, and 4, A, B, C, D, and so on. And we look at these and we say, okay, so this, in this case, A is true and B is true, right? And in this case, A is false, that is, not A is true, and B is true. So since these are the two possibilities, we disjoin these. And so if we were to construct a truth table for this disjunction, A and B, or not A and B, where we had A, B, and we had these, we put these down here, we would have under our main connective just this column. And so we say that this sentence that we constructed by applying the algorithm that we're given in the proof of metatheorem 6.2.1, was in the book, the algorithm tells us that this gives us this sentence when we apply the algorithm to this truth schema that represents a truth function. Okay, so I'd like you to have some sense of how to apply the algorithm. Maybe I would ask you, I don't know. I don't know. It's hard for me to predict what I'm going to put on a quiz a week from now. As far as the adequacy proof for the tree method, the level at which I want you to understand this is, what does it mean to say that the tree method is adequate? What are we trying to prove when we prove that the tree method is adequate? So what does it mean to say that the method is adequate? And recognizing that there are two parts to the proof, since the claim is a biconditional. And I want you to understand the roles of upward correctness and downward correctness. I want you to understand what it means to say that a rule is upward correct and what it means to say that a rule is downward correct. And these are defined in the handout clearly. And then have some idea of the roles that these concepts play in the two parts of the proof. So the upward correctness of the rules is significant in showing that if you have an open path through a completed tree, then the set is a consistent set. You need the upward correctness for that. And then the downward correctness, as we were just talking about, plays a role in the other direction, namely, if you've got a set that's truth functionally consistent, then the truth value assignment that makes those sentences true, the sentences that form the set, will make true all of the sentences along an open path through the completed tree for those set members. And it's the downward correctness of the rules that's going to ensure that. So just to make sure that you understand what we mean by upward and downward correctness, let's take a look at, suppose that we maintain the meaning of, say, conjunction. So this still has the same meaning. That is the meaning that we assigned to it or developed for it by means of its characteristic truth table. But suppose that instead, so this is the conjunction decomposition rule that we have for the ampersand, and it comes directly from the characteristic truth table for for the ampersand, right? But suppose we keep the same meaning, but we change the rule. So this, I think everybody recognizes both upward correct and downward correct. What does it mean to say that a rule is upward correct? That any truth value assignment that makes some list of conclusions true, that is something that's generated by application of the rule true, is going to make the sentence that generated those true, that list of conclusions true. So any truth value assignment in this case that makes both P and Q true is going to make the conjunction of P and Q true. Okay, what does it mean to say that it's downward correct? Any truth value assignment that makes the conjunction of P and Q true is going to make these guys true, the things that are generated by application of the conjunction decomposition rule true. Okay, so suppose that we change the rule, like, okay, no more this rule. Suppose now the rule we decide is this. When you see a conjunction of P and Q, you just write down P. So here's our newfangled conjunction decomposition rule. Is it upward correct? What do I mean by that? Again, a rule is upward correct if and only if every truth value assignment that makes at least one list of conclusions true, in this case there's only one list and it has one item in it, is going to be a truth value assignment that makes the thing that generated it true. So is it upward correct? Is it the case that every truth value assignment that makes P true makes the conjunction of P and Q true? Yes, right? Every truth value assignment that makes P true makes P and Q true, right? So it's upward correct. Is it downward correct? Again, what do we mean by downward correct? Again, this is all in the handout that I put this handout into Module 7, so it's handy dandy for you. Is it downward correct? Well, what do we mean by downward correct? We say that a decomposition rule is downward correct if and only if every truth value assignment that makes the thing that we're decomposing true, I'm calling that the premise of the rule true, makes at least one list of conclusions true. In this case, there's only one list and it has one item in it. Is it the case that it's downward correct? In other words, is it the case that every truth value assignment that makes P and Q true makes P true? Yes. Oh, actually, I take this back. Hold on. Let me go back to upward correct. I was being too quick here. Is it upward correct? It is downward correct, right? Is the rule downward correct? Is it the case that every truth value assignment, I had a little thinko there, I made a mistake. For downward correct, is it the case that every truth value assignment that makes P true every truth value assignment that makes P and Q true makes P true. Every truth value assignment that makes P and Q true makes, I hope some of you are thinking, what was she talking about a moment ago with upward correct? I'll go back to that in a minute. Every truth value assignment that makes P and Q true makes P true. Yes, right? If it makes P and Q true, it clearly makes P true, right? So it is downward correct. Let me go back to this. Is it upward correct? Is it the case that every truth value assignment that makes P true makes P and Q true? No, right? Because it could, suppose that you could have a truth value assignment that makes P true, but Q false, right? And that would make, if you had a truth value assignment that made P true, but it made Q false, then that would turn out to be false. So it's not upward correct, but it is downward correct. Let me do another example since my mistake no doubt confused most of the people who are listening to this, so I apologize for that. Let's look at another example. Okay, so our good old disjunction decomposition rule tells us this, that when you see a disjunction, it branches and you put the left disjunct on the left branch and the right disjunct on the right branch, okay? So now let's keep the meaning, again, we're keeping the meaning of the disjunction, right? We're keeping that, but we dump this rule, and in its place we have, so the new disjunction decomposition rule, say, is, let me think for a second, this one, P or Q, and we write down P and Q. Okay, so here's our new rule. Okay, but the meaning of disjunction is the same. So what now I want us to think about, is this upward correct? I'll be more careful now, sorry. Is this rule upward correct? In other words, is it the case that every truth value assignment that makes P and Q true makes P or Q true? And the answer is yes, right? Every truth value assignment that makes both P and Q true makes P or Q true. Right? By the definition of or. So if both disjuncts are true, then the disjunction is true. So the answer is yes. Okay. Let's think now about, is it downward correct? Again, I just want to make sure that you understand what it means to say that that rules are upward and downward correct. And sometimes what's helpful is to take a look at things that don't have the property, so you have a sense of what the property, what we mean by the property. Okay, is the rule downward correct? And so how would we think about that? Does every truth value assignment that makes the disjunction true, right? Because what we mean by downward correct is that every truth value assignment that makes the thing that you're decomposing true is going to make at least one list of conclusions true, and in this case we only have one list. So is it the case that every truth value assignment that makes P or Q true makes both P and Q true? And the answer is no, because you might have a truth value assignment that makes P true, but it makes Q false. And so that truth value assignment would make P or Q true, but it wouldn't make both P and Q true. It would make P true, but it wouldn't make Q true. Okay, so that's an example of a rule that's upward correct, but it's not downward correct. And because I made such a silly mistake in the first one, maybe we'll do one more. How about, again, we keep the meaning of the horseshoe is the same, right? It has the same characteristic truth table. And our good old upward and downward correct rule for the conditional is this. If we P horseshoe Q, it branches and we have not P and Q, okay? But suppose we dump that one. This one obviously is both upward and downward correct. And suppose instead we have the new rule for conditional decomposition, and it tells us that whenever we see a conditional, whenever we see a conditional, we have, say, I don't know, not P and not Q. Okay, so that's the new rule. Okay? And again, we're not changing the meaning of the horseshoe. So let's ask ourselves again, is it upward correct? So this is a branching rule, right? And so what does it mean to say that a rule is upward correct? A rule is upward correct if and only if every truth value assignment that makes at least one list of conclusions true makes the premise of the rule true. In other words, every truth value assignment that makes this true makes that true, and every truth value assignment that makes this true makes that true. Is it upward correct? Well, certainly every truth value assignment that makes not P true, that is, that makes P false, makes P horseshoe Q true. But it's not the case, not every truth value assignment that makes not Q true, in other words, Q false, that makes Q false, makes P horseshoe Q true. In other words, you could have a truth value assignment that makes Q false and it makes P true, and P horseshoe Q would be false. Okay? So the answer is no, it's not upward correct. Is it downward correct? And again, to say that a rule is downward correct, and this is in the, it's on page 2 of the handout. A rule is downward correct if and only if every truth value assignment that makes the premise of the rule true, in this case, the conditional true, is going to make at least one list of conclusions true. So in this case, it's going to make this true or that true, and I'm using or inclusively because it says at least one. So is it the case that every truth value assignment that makes P horseshoe Q true makes not P true, or, again using or inclusively, not Q true? Well, is that true? Is it the case that every truth value assignment that makes P horseshoe Q true is going to make P false or Q false? Again, no, right? Because you might have a truth value assignment that makes both P and Q true, makes P horseshoe Q true. So the truth value assignment that makes P true and makes Q true is not going to make either not P true or not Q true. So no, it's not downward correct, and no, it's not upward correct. So it's a doubly not correct replacement rule. Not that anybody would consider replacing this with that, but I just wanted to work through some examples of some rules that don't have all of the properties of being upward and downward correct, so you have a sense of what it means for rules to be upward correct. Okay, so if you replaced, so let's take a look at this one. This was upward correct, but it wasn't downward correct, right? This replacement rule for the disjunction. If you replaced good old disjunction decomposition with this new rule, it would really disturb the adequacy of the tree method, because if it's not upward correct, you're no longer guaranteed that having an open branch through a completed tree means that your set members are true, because it's the upward correctness of the rules that guarantees that. So if you have a rule that's not upward correct, oh wait, it was upward correct but not downward correct. But anyway, if it's not downward correct, then you're not guaranteed that truth functionally consistent set is going to have an open path through the completed tree. So if you have rules that don't satisfy both upward and downward correctness, then you're no longer going to have an adequate tree method. And depending upon whether it's not upward correct or not downward correct, it'll disturb one part or the other part, or perhaps both parts of the adequacy proof. Okay, this was the one where it's not upward correct, but it is downward correct, and that's the one I was thinking of. That disturbs the part of the proof that guarantees that if you have an open path through a completed tree, then you've got a truth functionally consistent set. Okay, because it's not upward correct. Okay, so I just thought I would mention those just to make sure that everybody understands what we mean by the correctness of the rules. And I'm going to stop here. What we're going to be doing next is we're going to be looking at Chapter 7. And after this, really abstract little interlude that we've had this week, I think everybody's going to be happy to be back down to kind of logical earth with chapter 7, when we're going to start learning what's called predicate logic. And you'll really like it. This will be fun. So I know that for some of you probably enjoyed this interlude. Some of you probably were like, oh my God, what's going on about the interlude? But regardless of what camp you might have fallen into, I think it was good for us to have done this. Because it kind of completed this section of the course, right? We started out by asking ourselves, what do we mean by a good argument? How do we distinguish the good ones from the bad ones? We need a standard. Then we had this standard, initially informal standard of validity. Then we firmed up that standard. We learned a formal language, and we made that standard more rigorous. So now we're talking about truth functional validity. And we actually developed, two methods, but eventually the tree method to test for truth functional validity. Given any argument at all, we can test to see whether that argument is truth functionally valid by constructing a tree for the premises and the negation of conclusion of that argument. And if the tree is closed, then we know the argument is valid. And if the tree is completed and open, then we know the argument is invalid. There's at least one truth value assignment that makes the premises true and the conclusion false. So what we did in this section, during this interlude, is we showed that, hey, that method actually does what we were using it to do. We proved in a rigorous way that the method actually does what we're using it to do, that there is an open path through a completed tree if and only if the set members form a truth functionally consistent set. So, it was good for you to have been perhaps dragged through this. So thank you for your patience, and next week we'll pick up and we'll move on to predicate logic, and you guys will really enjoy that, promise. Okay, bye for now.